Welcome to section 5 of genetics. In this section, we'll be discussing the Hardy-Weinberg principle. Let's get started. The Hardy-Weinberg principle is used to estimate the allele and genotype frequencies in a population. Don't get this confused with linkage equilibrium and linkage disequilibrium. As we discussed in a prior video, these are used when you're trying to determine the frequency of alleles associated with two or more genes. The Hardy-Weinberg principle is used to determine the frequency of one gene that has multiple alleles. So, for example, it can be used to determine the frequency of big A, little a, but not big A, big B. Big A, little a represent one gene with two alleles, whereas big A, big B represent two different genes. Finally, when using this principle, there are several assumptions, including no natural selection, no mutation, no migration, random mating, and large populations. So, no natural selection refers to the idea that there cannot be a selection pressure that makes one of the alleles less viable. No mutation means that one of the alleles isn't able to turn into a different allele. No migration refers to the idea that you can't have a lot of people with big A's leaving or coming into the population. Random mating refers to the idea that people won't be more likely to mate with other people who have large A's than small A's. So as I just said, the Hardy-Weinberg principle can be used to determine the allele frequency and the genotype frequency. For a gene that has only two alleles, P plus Q equals 1, which you can see right here. This is because we're assuming that there are only two alleles in the population. Therefore, all individuals will either have a big A or a little a, and the total percentage of individuals with big A or little a will equal 1, or be 100%. P refers to the frequency of the normal allele. This is denoted by big A, whereas Q refers to the frequency of the mutant allele, which is denoted by the little a right here. The genotype frequency can be determined by using the equation P squared plus 2PQ plus Q squared equals 1. In this equation, P squared refers to the frequency of individuals who are healthy. So their genotype is big A, little a. 2PQ represents the number of individuals who are carriers, so it's the carrier frequency. This is denoted by big A, little a. Finally, Q squared represents the frequency of individuals who have the disease, so their genotype is little a, little a. Okay, the easiest way to understand this is probably by going through a couple of examples. A healthy 27-year-old female presents to the physician for genetic counseling with her husband. They would like to become pregnant in the near future, but have concerns that their offspring may develop cystic fibrosis. The wife's sister has cystic fibrosis, an autosomal recessive disorder with an incidence of approximately 1 in 90,000 in this particular population. The husband's history is non-contributory. What is the probability of the husband being a carrier? Okay, so we're told that the incidence of cystic fibrosis in this population is approximately 1 in 90,000. In other words, this represents the frequency of individuals with the disease. From the Hardy-Weinberg equation, recall that the genotype frequency can be determined by using the equation P squared plus 2PQ plus Q squared equals 1. In this case, the frequency of the disease is represented by Q squared, so Q squared equals 1 over 90,000. The question asks, what is the probability of the husband being a carrier? From the same equation, recall that 2PQ represents the carrier frequency. So in order to know the probability of the husband being a carrier, we need to solve for 2PQ. We can do this by using the equation that I've already drawn on the screen in conjunction with the equation for the allele frequency, which is P plus Q equals 1. Okay, first we need to find out what Q is. We do this by taking the square root of 1 over 90,000. As a side note, you might think it's unlikely for this type of a problem to show up because the math for square roots can be complicated. However, you'd definitely be wrong in this assumption. For step 1, you need to know how to do simple square root math. The test is never going to give you a difficult square root problem, but you may be required to do math for simple square root problems. For example, the square root of 40,000, 90,000, and 160,000 can all be easily solved. In this case, we need to determine the square root of 1 over 90,000. 300 times 300 equals 90,000, so the square root is 1 over 300. So Q equals 1 over 300. With this information, we can solve for P by plugging Q into the equation P plus Q equals 1. By rearranging the equation, we get P equals 1 minus Q. If we plug in the numbers, we get P equals 1 minus 1 over 300. Solving for this, we get P equals 0.9967. Now that we know P and Q, we can multiply these by 2 to get 2 times P times Q. So you can see that I plugged in Q right here and P right here. So the probability of the husband being a carrier is 0.006587. You may have noticed that this math took quite a while to complete, and this is why on step 1, you should know how to do a shortcut to save time. With these type of questions, you'll usually be given very large numbers, such as 40,000, 90,000, or 160,000. In this case, the square root of 1 over 90,000 is 1 over 300, which represents Q. Because P plus Q equals 1, and Q is such a small number, in this case 1 over 300, we can assume that P must be very close to 1. So P is about 1. This is useful because it allows us to skip over several steps, and we can estimate that 2PQ is about the same as 2Q. In this case, we multiply 1 over 300 by 2. So 2 times 1 over 300 is 1 over 150, or 0.0066. Notice that this number is essentially the same thing as what we got before by doing a lot more math. So in summary, if you ever see a problem like this on step 1, first, take the square root of the incidence, in this case 1 over 90,000. Next, multiply this by 2. This number will give you the carrier frequency. In this case, it's 1 over 150, or 0.0066. As you can see, the math really is not that complicated if you take this shortcut. It will only require 2 simple calculations. So again, on the bottom of the screen, I've shown the complicated math, and on the top of the screen in green, I've shown the simple way to do it using a shortcut. Okay, let's do another question. As you can see, this is a continuation of the previous question. However, this time we're asked to determine the probability of the couple having an affected child. After going through the last question, we know that the probability of the husband being a carrier is about 1 over 150. In order to solve this problem, we also need to know the probability of the wife being a carrier. With this type of question, it can be useful to draw out a pedigree and a Punnett square. So let's do that now. As we learned from the question stem, the wife has a sister who has cystic fibrosis. So we can add this to the pedigree right here. With this information, we can determine that her parents must have both been carriers because this is an autosomal recessive condition. So let's fill in this Punnett square to reflect this new information. Because we know the wife is healthy and does not have symptoms of cystic fibrosis, we can eliminate one possibility from this Punnett square when calculating her probability of being a carrier. So she's not little a, little a. We're left with 3 possibilities. The probability of her being big A is 1 over 3, and the probability of her being big A, little a is 2 over 3. Okay, so we know that the probability of the husband being a carrier is 1 over 150, and the probability of the mother being a carrier is 2 over 3. Now we need to calculate the probability of them having a child who inherits both recessive alleles. So let's draw another Punnett square to represent this possibility. So if we assume both parents are carriers, we can see that the probability of having a child inherit an autosomal recessive disease is 1 over 4. Now, putting all of this information together, we get 1 over 150 times 2/3 times 1/4. This equals 1 over 900, or 0.0011. So the probability of this couple having an affected child is about 1 over 900. Okay, there's one more special circumstance which you need to be familiar with regarding the Hardy-Weinberg equation. In X-linked recessive diseases, the equation is interpreted slightly differently. For example, the equation for the allele frequency, so P plus Q equals 1, can be used to calculate the disease incidence in males. This is because males only have one X chromosome, so they only have one possible allele. Therefore, P represents the frequency of healthy males, or XY, and Q represents the frequency of males with the disease, or X subscript DY. The allele frequency for males can then be used for females. In other words, the P and Q values for males will be the same in females. The equation used to calculate genotype frequency, so P squared plus 2PQ plus Q squared equals 1, can be used when analyzing a disease in a female. In X-linked recessive diseases in females, P squared represents the frequency of females who are healthy, so XX. 2PQ represents the carrier frequency, so X subscript DX. Finally, Q squared represents the frequency of females with the disease, so X subscript D, X subscript D. Okay, let's wrap up this section with one more question. A 12-year-old boy has a history of easy bruising and severe joint swelling after minor injuries to his knees. This morning, he underwent a dental procedure and has had continuous uncontrolled bleeding since that time. Hemophilia A is suspected. This is a disease that affects 1 in 10,000 males. Based on this information, what is the incidence of this disease among females in the same population? Okay, so this boy has hemophilia A. This is an X-linked recessive disorder that results in easy bruising, uncontrolled bleeding after trauma or surgery, and bleeding into the joints, which can sometimes present as joint swelling in the knees. From the question stem, we learn that the incidence of this disease in males is 1 in 10,000. Because this is an X-linked recessive disease and males only have one X chromosome, we can conclude that Q equals 1 over 10,000. So remember, in the equation P plus Q equals 1, that Q represents the frequency of males with the disease. Because the allele frequency is the same in males and females, we can conclude that Q is also 1 over 10,000 for females. However, because females have 2 X chromosomes, they must have 2 diseased alleles in order to be affected by the disease. In other words, the frequency of affected females is equal to Q squared. So Q squared equals 1 in 100 million, which is the incidence of this disease among females in this population.